The Belizean Barrier Reef, largest coral barrier in the Atlantic. Located off the southeastern coast of the Yucatan Peninsula, the Belizean Reef forms a living barrier more than 100 miles long. Because of its size and associated patch reefs, the Belizean Reef system serves as a living model for understanding ancient reefs. Such a reef extended between the states of Texas, Louisiana, Mississippi, and offshore Alabama and Florida. Many ancient reefs, such as the well-known Capitan Reef of Permian age in New Mexico, contain oil and gas. Thus, knowledge obtained through study of modern reefs could aid geologists searching for energy reserves. To gain more insight into reef development, a team of U.S. Geological Survey scientists traveled to Belize to drill a series of core holes. The test holes were designed to decipher the three-dimensional history of reef development and enable us to map cements, which destroy porosity and permeability. The Belizean Reef forms a barrier which stretches in places for more than 20 miles without a tidal pass. A low ridge of coral rubble, typical of most reefs, extends along the seaward side of an extensive reef flat. The reef flat is covered by less than 5 feet of water. Tidal fluctuation is only about 6 inches, so the reef is seldom exposed to air. The seaward side in the foreground is buttressed with living finger-like projections called spurs and grooves. They dampen the force of storm waves. Base camp was the Smithsonian Institution's field station located on Caribou Key, 15 miles off the mainland. Test holes were drilled just off the island. A 60-foot core was drilled in 25 feet of water just seaward of the island, along with an additional 25 feet of core drilled through a reef spur. A third core was drilled landward of the reef crest, and another was drilled on the island. Several holes were drilled on and around a typical patch reef. The machine in the boat is a hydraulic power source, which drives a drill operated by divers using scuba equipment. It also contains a pump for circulating drilling fluid. The drill is a modified hydraulic wrench. Seawater is used for drilling fluid. It cools and lubricates the diamond drill bit. Muddy water is a positive sign that the bit is cutting and that circulation of fluid is maintained. It is a long and laborious task, especially underwater. Coring this hole to a depth of 60 feet took 28 hours. The core barrel is being brought up from 60 feet down. "100 pounds of barrel with its valuable core are lifted to the surface." Core recovery in coral reef limestone is typically 60% or more. Significant amounts of both cemented and uncemented sediment fill the open network between corals. Cemented internal sediment with steep dips such as this is common. Extremely hard rock is formed by cementation of internal sediment with magnesium calcite. This piece of core shows gray cemented internal sediment resting on white coral. Notice the dipping laminations. It is apparent that few geopedal cavity fillings in reefs are horizontal. The first hole was drilled in a groove. The second hole, drilled only to a depth of 25 feet, was located on top of the adjacent spur. A second hole was cored through a spur to determine how it formed. This spur was drilled to determine if it was constructed of coral or formed by erosion. It was found to be constructed mainly by lettuce coral. The third core hole was drilled to a depth of 30 feet on the reef flat just behind the reef crest. It consisted of reef sand and coral rubble with no evidence of submarine cementation. Drilling deeper was not possible because sand collapsed into the hole. The use of drilling mud was necessary to drill into the sandy island. Drilling mud cakes the wall of the hole and prevents collapsing of the surrounding sand. Clay dug from a stream on the mainland was brought out to the island, and a makeshift drilling mud was prepared. The mixture was forced down the hole with a small gasoline pump. The mud mixture's density also helps bring cuttings and sand to the surface. At 53 feet, solid rock was encountered. After drilling to 58 feet, the core barrel was recovered and the core removed from the inner barrel. A line is drawn to prevent misplacement of core sections. The rock is Pleistocene coralline limestone. It has been leached and altered to calcite. Characteristic brown caliche staining indicates that this limestone was once dry land. The barrier reef effectively dampens sea swells and waves. The result is a back reef lagoon free of significant wave and current action, conditions favorable for patch reef development. Typical patch reefs range from 100 feet to more than 4 miles in diameter. A mangrove island has sprung up on this patch reef. The water depth around this patch is 65 feet, and corals grow to the edge of the mangroves. The bottom is composed of lime mud. Much of the mud is derived from breakdown of the calcified algae that dot the bottom, here at 50 feet. The transition from lime mud to steeply dipping coral and carbonate sand is very abrupt. Digging with an underwater vacuum cleaner, called an airlift, revealed a transition from reef sands and corals to lime mud over a distance of about 4 feet. Numerous corals, principally staghorn and lettuce coral, cling tenaciously to the steep flanks of most Belizean patch reefs. A spherical coral, once dislodged, easily rolls down the steep slope. Samples of reef sands and lagoonal mud surrounding the reef were collected. On-site examination of washed portions were made for a rough determination of their composition. Under the petrographic microscope, we see that most sand grains are tiny coral fragments. The grains are produced by the biological breakdown of coral skeletons by boring sponges, algae, and the nibbling action of fish and echinoids. None of the sand-sized sediment was transported from beyond the patch reef. It was produced on the patch. The darker grains are coralline algal fragments. Those with tube-like networks are from the calcified green algae Halimeda. The field of view from left to right is 500 micron. We decided that drilling might help in understanding the evolution of a typical patch reef. In plan, or map view, core holes were located here, 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 and one in the center. A new method had to be developed to enable us to drill in 50 feet of water. Because of the depth, a diver can stay on the bottom no more than 1 hour to avoid the possibility of the bends. Such drilling would also be dangerous because of the soft mud bottom. Stirred up, the mud would obscure vision. To avoid these problems, the drill was suspended from 2 air-filled garbage cans. "30 feet of drill pipe were added so that the diver could remain at mid-water. Drilling was commenced by letting air out of the garbage cans. Recovery was made by adding air and floating the rig to the surface. More than 15 feet of sediment was encountered in all 4 flanking holes. The last core was taken near the center of the patch. Water depth is approximately 4 feet. Surprisingly, very little rock or coral was recovered. 43 feet of coralline sand were drilled before solid rock was encountered. What did the drilling show? A 43-foot section of uncemented coral and sand containing surprisingly little coral was found to cap a 20-foot topographic high. The rock forming the high consists almost wholly of recrystallized coral. You can see the calcite crystals sparkling in the light. This was probably a patch reef during Pleistocene time. The transition between coral and sand and lime mud is very abrupt. The upper 12 feet of sediment off the flank is lime mud and silt overlying 6 to 8 feet of terreginous clay. The Pleistocene rock is a lime wacky stone. At the transition, a 2 to 3 foot section of compacted peat was recovered. The peat, now 65 feet below sea level, has a radiocarbon age of almost 9,000 years. The reef's history is interpreted as follows. The area was once land, and vegetation flourished on clay soil and probably on the small hill. With rising sea level, about 9,000 years ago, the vegetation was smothered, and corals, which can only establish on hard rock surfaces, began to populate the small hill. Meanwhile, lime mud was accumulating. At a later time, with sea level even higher, coral and sediment production continued to build the patch upward faster than the lime mud. Finally, present conditions were reached. This reef resembles many reefs throughout the geologic record. It is easy to see how oil or gas might migrate from surrounding muds into the porous reef body to form a reservoir. In summary, cementation is restricted to a narrow band seaward of the reef crest. The reef flat is porous, uncemented carbonate sand, up to 1/3 of a mile wide and more than 50 feet thick. In this study, we have learned something of the geometry of a more than 100-mile-long barrier reef, which creates conditions favorable for patch reef development. You have seen that patch reefs can be localized by pre-existing topography. You have seen that the patch reef is composed more of uncemented carbonate sand than of coral framework, and that most of the sediment is locally derived by what is called bioerosion. You have seen some unique sampling methods. We hope that the research shown here will aid in deciphering geometry and porosity distribution in ancient reefs so that more vitally needed energy reserves may be found.